Welcome back to our podcast, where we delve into the fascinating world of data processing and the technologies that drive it. Today, we're focusing on batch processing, specifically how joins are implemented in Mapreduce workflows. If you've ever been curious about how massive datasets are efficiently processed, or how different teams within a large organization manage their data workflows, you're in the right place. So, grab your headphones, settle in, and let's dive in. In the realm of data processing, workflows often involve numerous batch jobs, especially when creating complex systems like recommendation engines. It's not uncommon to encounter workflows that contain anywhere from 50 to 100 Mapreduce jobs. Different teams within a large organization often run jobs that rely on each other's outputs, adding a layer of complexity that requires robust tool support to manage effectively. This is where higher-level tools like Pig, Hive, Cascading, Crunch, and Flume Java come into play, helping to streamline these workflows by automating connections between multiple Mapreduce stages. Now, let's break down the concept of joins. Joins are a fundamental operation in data processing, allowing access to records across different datasets based on their relationships. In relational databases, this is typically represented by foreign keys, while in document or graph models, the representation may differ. Joins become essential when you need to access related records, such as user profiles linked to user activity logs. While denormalization can reduce the need for joins, it doesn't eliminate them entirely. In traditional databases, indexes allow for quick record location, but Mapreduce operates differently. It lacks the usual indexing mechanisms, which means that performing a join often requires scanning entire datasets, an operation known as a full table scan. This can be costly if you're only interested in a small subset of records. However, for analytic queries that involve aggregating large datasets, this approach can be quite effective, especially when taking advantage of parallel processing across multiple machines. Let's visualize a typical join scenario. Imagine you have a log of user activities on a website, which serves as your fact table. On the other side, there's a user database containing user profiles, acting as a dimension in your analysis. To effectively analyze user behavior, you need to join these two datasets. Instead of querying the user database for each user ID found in the activity logs, an approach that would be slow and inefficient, you can optimize the process. A more efficient method involves extracting the user database using an ETL process and storing it alongside the user activity logs in a distributed file system like HDFS. This way, you can leverage Mapreduce to process and join the records efficiently. In this setup, mappers play a crucial role. They extract keys and values from the datasets, like user IDs from activity events and user profiles, and prepare them for the join operation. The key aspect here is that the mappers sort the data by key, ensuring that all relevant records for a particular user ID are grouped together for processing. This is where the concept of a sort-merge join comes into play. The mappers output key-value pairs that are sorted, allowing reducers to efficiently process all records with the same user ID in one go. The reducer first retrieves the user profile information, followed by the activity events, enabling it to generate the desired results, such as the ages of users who viewed specific pages. This architecture allows for high throughput and low memory usage, as the reducer only needs to keep one user record in memory at a time. The beauty of the Mapreduce model lies in its ability to abstract away the complexities of network communication, allowing developers to focus on application logic without the headaches of handling failures or intricate data retrieval processes. Beyond joins, another common pattern in Mapreduce is grouping records by key, akin to the SQL group by clause. This enables the aggregation of data, like counting records or summing values based on specific criteria. For example, you might want to count how many times a particular page was viewed or identify the top performing products. Another interesting application of this grouping pattern is sessionization, where user actions are analyzed over a session to understand behavior patterns. This is particularly valuable in A/B testing scenarios, where you want to determine if a new website version influences purchasing behavior. However, challenges can arise when dealing with hotkeys, keys that have an unusually high volume of related data. For instance, a celebrity on a social network might have millions of followers, leading to skewed workloads where one reducer has to process significantly more data than others. This can slow down the entire Mapreduce job as it waits for the slowest reducer to finish. To tackle this issue, there are algorithms designed to handle hotkeys effectively. One approach involves randomly distributing records related to hotkeys across multiple reducers while replicating necessary data to ensure all reducers have the information they need. This strategy helps balance the workload and improve processing times. Another effective strategy is using skewed join optimizations, where hotkeys are explicitly defined in the metadata. This allows for more efficient processing by separating records related to hotkeys from the rest, enabling faster joins through map-side processing. In summary, whether it's through sort-merge joins, grouping operations, or managing skewed data, Mapreduce offers a powerful framework for efficiently processing large data sets. The ability to bring related data together, optimize joins, and manage complex workflows makes it a cornerstone of modern data processing architectures. As we wrap up today's episode, we've uncovered the intricacies of batch processing and joins within the Mapreduce framework. From understanding how different teams manage complex workflows to exploring the mechanics of joins and the challenges posed by hotkeys, it's evident that efficient data processing is both an art and a science. Thanks for tuning in. We hope you found this discussion enlightening and that it enhances your understanding of how data processing works behind the scenes. Until next time, keep exploring the world of data. And remember, every dataset has a story waiting to be told.